When you sprinkle salt onto ice, the reaction feels almost unreal. The ice does not simply melt slowly like it would on a warm day. Instead, cracks appear, water forms instantly, and the structure seems to collapse from within. What looks like a burst of heat is actually a rapid physical process driven by changes in molecular balance. Under normal conditions, pure water freezes at exactly 0 degrees Celsius. At this temperature, water molecules arrange themselves into a rigid and orderly crystal lattice. Ice and liquid water coexist at the surface, constantly exchanging molecules. As long as this equilibrium remains undisturbed, the ice stays solid and stable. However, ice is never as solid as it appears, even at temperatures well below freezing. The surface of ice contains a microscopic layer of liquid water. Molecules at the surface are less tightly bound than those inside the crystal. This thin, invisible film plays a critical role in how salt is able to affect ice so quickly. When salt lands on ice, it does not interact with solid ice directly. Instead, it immediately dissolves into the thin liquid layer on the surface. The salt separates into sodium and chloride ions as soon as water is available. These ions interfere with the hydrogen bonds that hold water molecules in a solid structure. Once these bonds are disrupted, the freezing point of the water changes. Pure water freezes at 0 degrees Celsius, but salty water does not. With salt dissolved in it, water can remain liquid at much lower temperatures. This effect is known as freezing point depression and is the key to understanding the reaction. Because the salty surface water can no longer freeze, nearby solid ice is forced to melt. That melting produces more liquid water on the surface. More liquid water allows even more salt to dissolve. This creates a self-reinforcing cycle that rapidly spreads across the ice. This feedback loop is why the melting seems almost instantaneous. Melting creates water, water dissolves salt, and salt forces more melting. Each step accelerates the next one. Within seconds, the original solid structure of the ice begins to fail. As melting occurs unevenly, internal stresses build up inside the ice. Cracks form where the structure can no longer support itself, air pockets collapse, surfaces sink, and chunks fracture apart. These dramatic effects are mechanical failures, not explosions or chemical reactions. One surprising detail is that this process does not generate heat. In fact, melting ice absorbs energy from its surroundings. That means salted ice actually becomes colder as it melts. This is why salt and ice mixtures can reach temperatures far below freezing. Because of this extreme cooling effect, salt and ice mixtures have been used for centuries. Before modern refrigeration, they were used to make ice cream. In laboratories, they are used to demonstrate rapid heat absorption. The same physics applies whether you are in a lab, a kitchen, or outside in winter. This is also why salt is spread on icy roads. Lowering the freezing point prevents ice from reforming after it melts. Different salts are used depending on temperature conditions. Calcium chloride and magnesium chloride work better in extremely cold environments than regular table salt. So salt does not melt ice by warming it up, it melts ice by changing the rules that allow ice to stay solid. What looks like instant melting is really thermodynamics breaking equilibrium. Once that balance is lost, ice simply cannot survive in its solid form. That's it for today's video. If you enjoyed exploring with me, don't forget to subscribe to Science Lab, where we turn everyday things into scientific discoveries. See you next time.